Hello, I am Satyabroto. Welcome to my channel. If you like my videos, then please share and subscribe my channel and don't forget to click the bell icon. So today I will discuss resonance in chemistry. So concept of resonance was first introduced by Louis Pauling. So he was a great scientist and first resonance first concept of resonance was introduced by Louis Pauling. Okay. So now one question may arrive in your mind, that why resonance is required in organic chemistry or in chemistry. So answer lies here. So single Lewis dot structure, a single Lewis dot structure is unable to represent all the properties of a molecule. Okay, suppose I am drawing Lewis dot structure of carbonate, C double bond O. So I am representing electron by red dot. One, two, three, four, five, six, seven, eight. Yes. So here we have to put a negative charge on oxygen atom. Same here, we need to put a negative charge on oxygen atom. So there are another two Lewis dot structure of this CO3 2 minus. Okay, so now we need to think in this way, that this, if I designate, if I represent the bond, this is A, this is B, this is C. See, A, C double C, the A bond between carbon and oxygen, here it is twice, it is single bond, and once it is double bond. This is same for in case of B, same, twice it is single bond and once it is double bond. In case of C, twice it is single bond and once it is double bond. So that is why a single Lewis dot structure is not able to represent all the properties of a molecule, because sometimes carbon and oxygen is single bond and sometimes it is double bond. So because so here negative charge actually dispersed all over the three oxygen atom, and that is very important. We can say that negative charge is dispersed over all three oxygen atom. Clear? So to represent this phenomena, we need resonance, we need to study resonance. Okay, so I think you have all understood why resonance structure is required, because when electron is dispersed over the system, then properties will change, properties changes, molecular properties changes. Okay, so definition of resonance, we can say resonance structures are drawn by shifting of pi electron without changing the position of nucleus, and actual molecule is weighted average. This weighted average is very important, weighted average of all possible canonical structure, and this phenomena is resonance. Okay, now I will draw two canonical structure of benzene. This is Kekulé structure 1 and this one is Kekulé structure 2. And Kekulé is the name of a brilliant scientist. Okay, he gave the idea of structure of benzene. Okay, so Kekulé structure 1 and this is Kekulé structure 2. Now, two structure can be derived only by the shifting of pi electron. See, these two structures can be derived by shifting of pi electron. Here we have I have shifted the pi electron. Okay, then see, we got this structure. This is pi bond. We have shifted this pi electron, then we got a new pi bond, and we have shifted this pi electron, so we have another new pi bond. So see, this Kekulé structure 1 and Kekulé structure 2, you can draw these two structures just by shifting of pi electron. And now I will show you some bond length. Okay, what will be the bond length of CC bond length? Okay, CC bond length uh, 1.48 angstrom for sp2 carbons. CC bond length is 1.53 angstrom for sp3 carbon, and C double bond C bond length is 1.34 angstrom for sp2 carbons. But okay, but CC single bond length in benzene, CC single bond in benzene is 1.39 angstrom. Okay, so how will you define this bond length? Because CC single bond is 1.48 angstrom for sp2 carbon, CC single bond length is 1.53 angstrom for sp3 carbons, and C double bond C bond length is 1.34 angstrom for sp2 carbons. But CC bond length in benzene is 1.39 angstrom. So actually this 1.39 angstrom, that is it is in between these two. So because here if you see the Kekulé structure 2, here this bond is double bond, but here this bond is single bond, because sometimes it is single bond and sometimes it is double bond. So bond order is 1.5. That is why CC bond length in benzene is 1.39 angstrom in between CC bond length for sp2 carbon and C double bond C bond length of sp2 carbon. This is in between these two. Okay, that is why we should consider the average structure, where the 6 pi electrons are distributed over the all 6 carbon atoms. This is sigma skeleton of benzene. Red orbitals are sp2 and blue orbitals are 1s1 of hydrogen. So this is sigma bond. These are all sigma bond. These are all CC sigma bond. These are CC sigma bond and these are CH sigma bond. These are CH sigma bond. Now I will draw the pi skeleton of benzene, because if I show you the sigma skeleton and pi skeleton in a single picture, then picture looks very messy, so I don't want it. These are the p orbital, unhybridized p orbital. These are the unhybridized p orbital. I am showing it by green color. Okay, I am drawing the pi electron here, p orbital. Because in for sp2 hybridization, we have unhybridized p orbital, and which involves in pi bonding. This is pi bond. This is pi bond. And this pi bond is perpendicular to the plane of sigma skeleton. So that is why I don't want to draw the sigma skeleton, pi skeleton in a single picture, because here picture looks very messy. So here it is very clean. Okay, so this is pi bond, this is pi bond, and this is pi bond. So one can get the other Kekulé structure just by shifting the pi electron. Just by shifting the pi electron. So if the here structure is this one, this is the Kekulé structure, but if you shift the pi electron in this way, then you will get this one. Okay, this is Kekulé structure 1, this is Kekulé structure 2. So here obviously 6 pi electron, this 1 2 3 4 5 6, these 6 pi electrons are delocalized over all 6 carbon atoms in benzene ring. This is very important. Now we can say that during the phenomena of resonance, it is found that the determined energy of actual molecule is less than estimated energy of any of the canonical forms, and the consequence of this is that stabilization is the result of resonance. And when I have given the definition of resonance, where there I have said one word, that is weighted average. Weighted average means that the canonical structure which is the most stable one, that will contribute to the that will contribute more to the overall structure. Okay, got it? Now resonance energy, because for resonance molecule gets stabilized, so resonance energy is estimated energy of the most stable one, most stable canonical, minus determined energy of actual molecule. Obviously I will give you a separate videos on resonance energy. There maybe I think you will get more clear picture. Okay, now we need to remember some points to draw the canonical forms. First point is, all the canonical forms must be a bona fide Lewis-Dot structure, and this is very important, bona fide Lewis-Dot structure. And canonicals are drawn by shifting of pi electron without changing the position of nuclei. So here, what do you mean by bona fide Lewis-Dot structure? Now, if because here I can give you one example, that is, you can't compare resonance hybrid of hypothetical cyclohexatriene. So what is cyclohexatriene? Say suppose this is cyclohexatriene. So here we are assuming that these double bonds, these three double bonds are not localized. Okay, if they are not localized, then we can say this is cyclohexatriene, because as these three double bonds are not localized, then the bond distance between CC single bonds and C double bond C are not same, because they are not localized. So you can't shift the pi electron here. Okay, you cannot compare with benzene. Okay, we cannot compare it with benzene because they are not equal, because bond lengths are different in both cases. Second point is another important, this is very important, involved orbital, or pi electrons must be in a plane, Here I am drawing the 1,3-butadiene. This is p orbital or 1,3-butadiene. So this is double bond and this is double bond. So now involved orbital, because here these two p orbitals, I am coloring it by red. Okay, these two p orbitals are involved in resonance and they are in plane. Okay, now these two orbitals, this red, this green and this red, they are also in plane. Okay, so just assuming that all p orbitals are perpendicular to the plane of the paper. Okay, this red and this green, they are in the same plane, and this green and this green, they are also in the same plane. Okay, just I have shifted pi electron in this way. Clear? So now the resultant next canonical structure will be this. These p orbitals are now vacant, so we need to put a positive charge, and these p orbitals contains these two pi electron, bonded pi electron, so we need to put a negative charge. And they are forming the double bond. Okay, so see, this molecule is neutral and this molecule is also neutral, because here it contains one positive charge and negative charge, so as a whole molecule is neutral. So if your molecule is neutral, then each canonical should be neutral, mind it. Okay, and all the canonicals, the next point is all canonicals should have same number of paired electron, paired or unpaired electron, because otherwise the magnetic property will change. Otherwise the magnetic and other electronic property will change. because we know that, because when the molecule is paramagnetic, then we think that number of there should be unpaired electron, because if one canonical contains unpaired electron, another canonical contains no unpaired electron, then so one is paramagnetic, another is diamagnetic, so it is not possible. So that is why all canonicals should have same number of paired and unpaired electron, otherwise the magnetic property and other electronic property will change. Okay, now I'll give you like I'll give you three schemes that those are very important to draw the canonical structures. Okay, first case, so just you need to remember this skeleton: X double bond Y single bond Z. Okay, just I'm giving examples with ABCD XYZ. This is very simple. This is very simple. It's a pi bond, and Z contains also a p orbital, and some you need to consider positive charge on Z or negative charge. If when it is positive charge, then this p orbital is vacant, will be vacant. When it is negative charge, then these p orbitals should contain a pair of electron, and when it is unpaired, then we need to consider one electron in the p orbital of Z. Clear? First case, we are assuming that Z contains positive charge, means Z is vacant. The p orbital on Z is vacant. Case 1, positive charge, where p orbital on Z is vacant. Okay, just considering this framework, you can draw any canonical structure. Believe me, you can draw any canonical structure. X double bond Y Z. Okay, so Z is vacant, so we need to put a positive charge. So as we know, involved orbitals should be in a plane. These two orbitals are in a plane, and this p orbital on Z and this p orbital on this p orbitals on Y and this p orbital on Z are also in plane. So we can shift pi electron in this way. Then the double bond is in between Y and Z, and p orbital on X is now vacant. Now positive charge gets shifted from Z to X. Okay, now we'll apply this to draw the canonical structure in benzyl cation. Just see. This is CH2 plus benzyl cation. Now just this is X, this is Y, this is Z. We are shifting pi electron here. Just I am mimicking. I have shifted pi electron. Then what will happen? This carbon now bears positive charge. Okay, and the other double bonds will be intact, and we'll have a new double bond between this carbon and this carbon. Okay, now again I am mimicking the XYZ skeleton. X double bond Y Z. Here Z is positive charge. Now I am shifting the pi electron from between X and Y to Y and Z. See, here I am doing the same thing. The other double bonds will be intact. The pi electron, this pi electron is now here, and the positive charge gets shifted from this carbon to this carbon. Okay, now again I am considering x double bond y z plus, same thing. Then the next canonical structure, the pi electron, this pi electron now moves here. The other double bonds are intact. This double bond and this double bond will be intact. And positive charge gets shifted from this carbon to this carbon. Okay. The next canonical structure, again to draw the next canonical structure, I am following the same rule. X double bond y z plus. Clear? Then the resultant canonical structure will be this one. These two double bonds will be intact. These two double bonds are intact. We are not changing the position of these two double bonds. Now yes, so positive charge gets shifted from this carbon to this carbon, and the double bond, new double bond is this one. So now this will be CH2 plus. Okay, so 1 2 3 4 5, these are the all 5 canonical structure of benzyl carbocation. Okay, and we are drawing in the using very simple scheme, x double bond y z plus. Now we'll consider case 2, where where negative charge resides on p orbital of z. Okay, the case 2. Case 2. So in case 2, x double bond y z bears negative charge. So z contains two unpaired electron. So sorry, z contains paired electron. Okay, and the x double bond y is the pi electron. Now to draw the canonical structure, because all the involved orbitals are in a same plane, so we are shifting this pi electron between x and y to y and z. In the resultant hydrogen structure, in case 2, x double bond y z, z contains paired electron, and there is a pi electron forms double bond between x and y. Now we will shift this paired electron between y and z. So here now pi electron is forming between y and z. So as pi electron forms between y and z, then these pi electrons between x and y now move on p orbital of x. Now resultant structure will be, now x bears the negative charge. So negative charge gets shifted from z to x. Now x bears the negative charge, and the double bond is now between y and z. Okay, so now I will consider, now I am considering this framework to draw the canonical structure of benzyl anion. In benzyl anion, what is benzyl anion? pH, this is pH phenyl ring, CH2 minus. Okay, So again I am considering X double bond Y Z. Okay, so bonded non-bonded electron pair moves between Z and Y to form the new pi bond, and the pi bond between Y and X breaks, and the pi electron moves to X. Same way, now negative charge gets shifted from this carbon to this carbon. The other pi electron will be intact. This and this are intact. Now negative charge resides here. The new pi bond, this one. Now again I am considering X double bond Y Z minus. Same way, just I am mimicking. This pi bond, this double bond and this double bond are intact. Now negative charge gets shifted from this carbon to this carbon, and then there is new pi bond. Simple. Then again I am considering X double bond Y Z minus. Okay, so this double bond and this double bond are intact. The newly formed double bond, this is the newly formed double bond, and the negative charge gets shifted from this carbon to this carbon. Again I am following this one, X double bond Y Z minus. This then resultant structure is this one. That is how we can draw the canonical structure. We can draw the canonical structure in a very simple way. Okay, so you can draw the canonical structure of phenol, aniline. Okay, using this framework. Okay, so here X double bond Y Z. So see X double bond Y Z minus. Instead of Z minus, if there is lone pair, that is also okay, because here in oxygen two non-bond, two lone pair. So one lone pair will involve in the resonance. You can consider. Okay, here nitrogen contains only one lone pair, and this lone pair are involved in the resonance. Okay, so that is why you can use this framework to draw this type of canonical resonance structure of aniline, phenol, or anisole. Okay, and try to draw the canonical structure in home. Okay, case 3. In case 3, one unpaired electron is on p orbital of Z. So X double bond Y Z dot. It is very useful to draw the canonical structure for free radical. Z contains one electron. To draw the resonance structure, here we need to follow the Fish-Hook arrow, because Fish-Hook arrow indicates the transfer of one electron. We know that 2 electrons are required to form a pi bond. So now unpaired electron is on X. And the double bond is now between y and z. Okay, because arrow notation indicates this one. Now we'll use this framework, this scheme, to draw the resonance structure of benzyl free radical. CH2 dot, the same way, because here it is like x double bond y z dot, now it is x dot y double bond z, so x double bond y z dot these two double bonds don't involve resonance, so we are not changing the position of these two double bonds. CH2, only this position of double bond changes, this position of this double bond changes. Okay, so now unp electron now moves from this carbon to this carbon, then again x double bond y z dot the follow how I am drawing. This is very important. These two double bonds are intact. Now this double bond moves here, this double bond moves here, and that unp electron moves from this carbon to this carbon. Now again x double bond y z dot okay. And again x double bond y z dot. These two double bonds don't involve here, so only this double bond position of this double bond changes. Okay, so this is how we can draw the canonical structure in a very simple way, just using this framework. Okay, so thanks for watching this video. Okay, so if you like this video, make sure to subscribe for more. Bye.